All right, so this is going to be my guide to the practice exam. I'm just going to try to do this all in one go and see how long it takes me. Might skip a couple of extra questions, a couple of questions if if they're too much repetition. So here we go. So the very first section is the atomic structure section, and they have asked me about giving the SPDF notation for the following elements and ions. First one they've chosen is iron, so I'm going to go over my trusty periodic table over here. Think about iron, it's element number 26. So it looks like it's in row 4, so I need to have all of the S's up to 4. So here I'm going to go 1s2, 2s2, 2p6. So that's my first 2 rows worth of electrons. The first 10 there, 2p6, 3s, 2. We go 3p6. That's my fourth row, my third row done, and then we're gonna go 4s, and I'm gonna have 5d, or no, not 5d, sorry, 3d as well. So these are my 3d electrons. This is the tricky part. We have to go and count up the electrons. So I'm gonna count iron's position amongst that row. 1, 2, 3, 4, 5, 6, 7, 8. It's 8 in from the left from 4. So that means that if I give it 4, if I fill normally, I would go 4s2 and 3d6. I'm gonna think about that. Okay, am I close to half the d orbital? Do I have 4 d electrons? If I had 4 d electrons, I might consider borrowing from the 4s orbital. But I do not have 4d electrons. I have 6d electrons. That's a pair number. That's an even number. That's a pretty stable set of electrons. Now, I mean, one of the things that's fun about iron is that we can think about iron's 2 oxidation states. It has a +2 oxidation state, which would be canceling out these electrons or losing those ones. That makes sense. Largest orbital. The 4 in front here indicates the largest orbital. And then the other most common oxidation state is 3+. Well, 3+ would be reducing this one down to 5. Oh, look, that's that half-filled d orbital. A half-filled d orbital is the stable kind of orbital, so that's where that makes sense. Okay, well, I'm going to go on to my next question, that one that's actually asked. Okay, so this is magnesium. Magnesium's number 12. This is a straightforward one. This is simply 2s2, 2p6, just all the first 2 rows done, and then we just have 3s2. It is in the S block. Magnesium is considered S block. That means the first 2 columns, that's our S block. That means the last orbital you're going to fill is going to be an S orbital for those. D block, last orbitals you're going to fill are d orbitals. P block on the right is last orbital filled is a p electron. Okay. So nickel, right in the middle of the periodic table again, just 3 over from iron. So actually, if you're, if this was something we could do on the exam, this would be a great trick, is you could just copy this, right, and paste it. And we say, okay, but it's got 3 extra electrons. So I'm going to go over here, go to 3d orbital. I'm going to put in 3 extra electrons. That makes 9. Now, if this was nickel, if this was normal nickel, I would say, whoa, wait a second. I got a 3d9. That means I'm 1 electron short of a full d orbital. So energetically, it would be much better to borrow 1 electron here and borrow 1 electron into the smaller but less energetically stable orbital, the 3d orbital. Okay, so that's stable nickel, but they have asked about nickel 2+. And so because nickel has this sort of partial 4s orbital, we do know that we need to, I'm just going to double check that. That looks like I have the wrong number of electrons. See, this is going to be the problem. I'm going to do this video in one go, and I just realized that I miscounted. If you do miscount, nickel's only 2 more electrons, not 3 electrons. That would have been copper. Okay, well, so go back, step back here. We're going to have a 3d orbital that has 8 electrons in it. And the 4s orbital is going to have 2 electrons. Okay. So now we're going to lose 2 electrons. The 2 electrons that get lost, this is going to be the most common mistake, is that students are going to take them out of that 3D orbital. No, no, no. We have to go largest orbital first. So largest orbital first means that to get a +2 state, you must lose the electrons out of that 4s orbital. You can either write 4s0, or a more probably correct way is just to erase the 4s as if it wasn't there. Even though we fill electrons in a certain order, when we lose electrons, we lose them largest orbital first. Okay, so let's do the chromium. Chromium is chromium is 2 smaller than iron, so I should probably need to stop cheating. Maybe that's where my mistake is. Okay, so I'm going to just go, okay, chromium is in the 4th row, so I'm going to set up for a 4th row element. That means all of the electrons before the 4th row are set in stone, they're filled. So I only care about this 4s business and the 3D. Let's count how many electrons it is. So we got potassium, calcium, scandium, titanium, vanadium, chromium, or 1, 2, 3, 4, 5, 6. So I have 6 electrons. So that means that I would normally go 2 and 4. And that should raise some alarms because I see that 4 on the d orbital. This is a borrowing case. So this is a case where we should be borrowing to fill the 5d. Okay, now that I've established what electrons are where, now I can take my oxidation into account. How many electrons is chromium going to lose? Well, we're only losing 1 electron, and that 1 electron's got to come out of either this orbital, that one, but we know that 4s is the larger orbital, so this is the one we remove. So I'm going to just erase that. Bye-bye. And this is my final setup. As I said, you could also leave the 4s0. That would be fine. That indicates you understand something, I guess. So either way, that would be fine. I wouldn't have any problems. Okay. So the next section is the box notation. So this is where we're going to draw boxes for each of the orbitals. And I did say you can use noble gas shorthand if you like. So that can save you quite a bit of time. But we'll write it all out. So what we're going to do for oxygen, for example, oxygen is in the 2nd row. So I know that I have a 1s orbital, I have a 2s orbital, and then I have my 2p orbital. And I have, for oxygen, I've got 8 electrons. So let's fill in those electrons. Remember to go up, and then down, up, and then down, and then up, and then up, and up. We have to fill every single box first, and then for one set. And then if we have any extra, so 1, 2, 3, 4, 5, 6, 7, I only have 7 done so far. I do need 1 extra electron. Okay, so let's do the same thing for phosphorus. That one took up a little bit of space, so I'm going to shrink it. Looking at this now, I guess I should, maybe if I write this kind of question, I'll have to make sure I give more space next time. Okay, so let's get some boxes in here. You could do something like this with a ruler. Apologize. So you could come in and put some boxes like this. Trying to save myself a little bit of time here, so I'm gonna go. Yeah, that's gonna be my first S. Second S, these will be my 2 P's. A little break here. 3S. And then my 3P. Okay. So this will be 1S, 2S, 2P. You don't have to label X, Y, Z, even though that's what they do have names. 3S, 3P. Okay. And now I'm going to get my electrons out. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Why do we fill it out that way? Well, of course, because of the Pauling exclusion principle. Or no, Hund's rule. Hund's rule? Oh, well, one of those rules. Make sure you review them. Okay, so it's a P minus now. So that means that we only have one extra electron. Normally, it has as many electrons as nitrogen, which would be 1, 2, 3, 4. It has 15 electrons. So let's see if I can count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So normally 15 electrons. And then with that only that one extra negative, we're just going to drop that in and make it upside down. So it has sort of a oxygen setup now. Sort of a weird question. I don't know. I think we could have picked a more interesting element to get some more interesting filling, but I'll leave it there for now. Thinking about, chlorine minus would have been more interesting maybe, or sulfur or something like that. But okay. Let's do the zinc or the zirconium. So zirconium's way over here. It's way down in row 5. So I think we're going to need, I really think that drawing all that's going to be a real pain. So I'm going to do the quick notation. So that's krypton for the row 4 noble gas. And then I'm just going to focus on row 5 orbitals. So row 5 orbitals is the 5s and the 4d orbital. So those are the two I need to draw out. And I'm realizing that I really did not give students a lot of space on this test that I wrote. It was so long ago. I think I might have written this test in my first year of teaching. So it's not the most nicely made test, but the questions are still okay. So I'm going to draw out my diagram here. I've got the 5s orbital here. Don't know why I did it this way, but that's okay. And then I've got my 4d orbital. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, get some electrons going. So normally zirconium is number 1, 2, 3, 4. It's number 4 in the row. So we would normally expect 1, 2, 3, 4 electrons in zirconium. Okay, so that looks all right. And now it is a 2+. So I need to remove 2 electrons. This is where students will again make a very common mistake. They'll look at this setup and they'll say, well, I should take the 2 electrons from the orbital that's the farthest to the right because that's the one I filled last. But again, the same idea. It has to be the largest orbital that loses electrons first. So if you're losing 2 electrons, 1, 2 electrons. So there should be this sort of gap. So anytime that you have a d metal, you're going to lose those s electrons first, then start losing the d orbitals. Okay, that's that question. All right, so consider 2 electrons with the following quantum numbers. Which electron is farthest from the nucleus? Explain. Which electrons cannot exist? Explain. And which electron is in the simplest orbital? So simplest here means the least complicated orbital, or the least features, I guess. So which electron is farthest from the nucleus? So farthest from the nucleus is going to be the largest n value. So I'm going to go here, the n value of 3. Yeah, so that's the only electron that has n value of 3. So let's say this. So electron 3. I think I can get rid of this for now. Okay, electron 3, n equals 3, so that, or electron 1, sorry, electron 1, n equals 3. This is n is proportional to the average. Okay, should just come with AVG, to the average distance from nucleus. Okay, which electron cannot exist? All right, this one's going to be trickier, so let's look around here. We've got an n equals 2, l equals 0. So far, so good. If l equals 0, we're talking about an s orbital. So can ml equal 1 for an s orbital? That doesn't sound right. Doesn't ml have to be either equal to the value of L or any integer between it and its positive and negative? I believe so. So if we think about it, we can say, for n equals 0, we have L equals 0 and ml equals 0. N equals 1, then L can, there is no n equals 0. L is always 1 less than 0. Okay, so n equals 2. L is equal to either 0 or 1. And if L is equal to 0 or 1, then ML is equal to either 0, so that's another s orbital, or ML, it could be plus 1 or even minus 1 or 0, right? Because this is our p orbital here. L equals 1. So this is, boy, it's been a long time since we had to talk about this, eh? And this is s. So L equals 0 is our s orbital. There's only one s orbital. P equals 1. L equals 1 is our p orbital. And then there are 3 of those, from plus 1 to minus 1. Okay, so I think we found it. L equals 0 cannot be that value. So let's just double check to see if there's any other mistakes. We've got an L equals 1 for an n equals 2. That should be fine. We have an ML is 1 on that one. That's fine. All of the MS values so far seem fine. N equals 2. That's no problem. We can have L equals 0. As long as L is 0, if L is 0, ML is restricted to 0. That's fine. And then electron 5 is fine as well. Okay, so nothing too exciting there. So the only electron that can not exist is electron 2. Electron 2. And so the reasoning would be that ML cannot be of larger magnitude than L. So so for L equals 0, ML equals 0. That's probably a good answer. Or if you just, even this is a good enough explanation right there. That's the most important part. Which electron is in the simplest orbital? So simple orbitals would be low L numbers and low N numbers, and particularly low ML numbers would actually be the important part. So a low L and a low ML indicate a particularly simple orbital. So right here we have a L equals 0, ML equals 0. That's an s orbital. Do we have any other s orbitals? No. This one here is a p orbital. So that's a p from the ML value. This is the L value and the ML value. The L value gives us a p orbital. This electron number 2 doesn't exist, so that one also is in a simple orbital, L equals 0, but the ML value doesn't exist, so it doesn't work. So the only answer that makes sense is electron 4. I'm looking back at this question thinking, what was I thinking asking this? This is a pretty tough question, I think, especially on a final exam. But, well, maybe the next one won't be so obscure a question. Okay, so for electron 4, L equals 0, which indicates a simple s orbital. The really in-depth answer here is L is a measure of how many nodes, and so this is the least number of nodes. L measures number of nodes. So L equals 0 is simplest. So if we were thinking about our wave dynamics, this would be L equals 0 is a simple standing wave. So think about a skipping rope, spinning a skipping rope, and then L equals 1 is a more like a sine wave. And L equals 2. I don't even remember if we covered this in class, but I'm, using this opportunity to talk to some of you about how awesome this whole concept is. I love this unit so much. Oh well. Anyways, which element is most electronegative? So I'm going to need that periodic table back. So let's see if I can pull that up. So I've got silver over in the middle of the back end of the d orbitals. I've got magnesium a couple rows up over in the alkali metals. I've got scandium. Scandium is on the right, isn't it? No, left. It's way over on the left again. And I have indium, or I have iodine, which is down on the bottom of the halogens. And I have sulfur. The rule of thumb is the element that is closest to fluorine is the most electronegative. So that would be sulfur as the winner. So sulfur is closest to fluorine. So is most electronegative. Okay, remember electronegativity increases from cesium to fluorine. All right, which bond is expected to be the most covalent and non-polar? So to get a non-polar and covalent bond, you'd want two elements that are very, very close together, and have the least electronegativity difference between them. So covalent, non-polar. So this would be lowest electronegativity difference. And this is supposed to be a strikeout in the park kind of thing, and you're supposed to knock this ball out because there's only one of those is a pair of atoms that are identical. This is a true ionic bond. It's lithium and chlorine, so this is an ionic bond. These are two metals, so this would actually be metallic bonding, which I don't even think we covered. Metallic bonding. But it's a sort of special bond. Boron and fluorine and carbon and oxygen are both going to be polar covalent bonds. These are both polar covalent because they are both non-metals. At least we can guess. We could get the electronegativity difference and really confirm, but the carbon-carbon bond has no electronegativity difference. They are exactly identical. Negativity difference. So will form true non-polar covalent. There's a whole side topic in there, but that's okay. Okay, so this the year I taught this unit, this course, and made this exam review, I had separated out one of the units called aqueous reactions, which we didn't do specifically, but we did it as mixed in with our electrochemistry unit and with our solubility unit. So this section we're going to do, this section is a little bit different from how we did it earlier, but anyways. That's the only reason this is its own separate section. But these are definitely topics we covered at some point, so let's see if we can do it. We have, I'm going to leave the hardest one for last. So I'm going to start with this nitrogen in calcium nitrate. So I've got a calcium, and we have NO3, 2. Okay, so we put in the elements that we know, +2 for calcium, -2 for oxygen, and then we start multiplying. So we've got a +2 here. We've got 3 times the oxygen, but there's some crazy stuff going to happen here. We gotta have to kind of think about this as the 2 multiplied by the n. So we actually kind of have n2 and then 2 times 3, so that's 0.6. So just kind of separate those out, even though they're not written out that way when we're doing this calculation. Minus 2 times 6 gives us minus 12. So I need positive 10 for my nitrogen. Divided between the 2 gives me a plus 5. So the nitrogen is plus 5. Okay. If you need me to slow that down, too bad. This is a video. You can't ask me any questions. That was a joke. Okay, so let's carry on. We have potassium, that's a plus 1. We have oxygen, a minus 2. So again, we're going to multiply by the subscripts. Minus 2 plus, it gives us minus 8. Plus 2, the plus 1 times 2 gives us plus 2. That means the molybdenum must fill in the difference. And that means it must be a plus 6. So plus 6. So as long as this was really clearly written, I would be totally fine with even just doing the little doodles on the diagram here. But you just got to be really clear with how you write it. Okay, this one's an ionic one. So this one's a little bit trickier. So let's see if we can do it. We've got UO2OH4. So this is going to be pushing the boundaries of anything we've ever done before. And it's also minus 2 minus. So this thing doesn't even add up to a neutral charge. So I probably won't ask this question this year. I don't know why I felt so confident I could ask it on the year I made this exam, but whatever. Okay, so I've got hydrogens that are plus 1, so that gives us a plus 4. Minus 2 times 4 gives me a minus 8 from the oxygens in those hydroxide groups. We have a minus 2 from this other oxygen pair, so that's going to give us a minus 4. And then the whole thing adds up to minus 2. Okay, so we add it all up together. We can see that we are getting close. We got this cancels out. We got a minus 8, and it has to add up to minus 2. So what is missing over here is another one of those plus 6s. So plus 6. One thing you can always go and check, if you don't have oxidation states on you remember the oxidation states are imaginary. So we should double check to see that uranium even can have 6 electrons. So we see it's number 92 over here. And that means that we got francium, radium, actinium, thorium, protactinium, uranium. So 1, 2, 3, 4, 5, 6. That's 6 electrons. We can kind of think about that. That's the 6 electrons in its valence shell. It definitely can have the plus 6 state. Cool, cool, cool. You can't really have an oxidation state that's higher than the number of electrons you have to donate. So there is that little rule there. Okay, so the next section, it says, give the expected reaction between a silver nitrate and magnesium chloride solutions, the ionic equations, and net ionic equations. So here we're going to write out silver nitrate plus magnesium chloride. And boy, look how sloppy I was. I didn't even include the 2 in that chloride. That's bad habit there. And so we need to check its solubility. So this is where you could use your basic solubility table. So here's my solubility chart. And I think about the products here. I'm going to get silver chloride. And I'm going to get magnesium nitrate. 3, 2. And I can balance that. I'm going to need 2 of those. And that's that. I'm going to get 2 of those. Okay. And then we go and we look up our chlorides. Chlorides here on our negative ion chart is low solubility with silver. So that is the one that will be solid. And the other one will be aqueous. Magnesium chlorides are aqueous. And silver nitrates are aqueous. So we get to start with aqueous. So then it does ask for net ionic equations, ionic equations. So that means we need to do a little bit of work here. So remember that our ionic equation means that the aqueous system is going to be split up. So anything that is considered aqueous will be split up into its ions. And so that means the magnesium 2 as well. And then anything solid will be stuck together. So silver chlorides, these will be solid, but the magnesium ions will remain as spectator ions. And watch out those phase symbols. We got to write out all so many phase symbols. Now, as long as you balanced it beforehand, this is no problem. And then we are going to remove anything that is on both sides of the table. So both of these are found right here. So the actual reaction that we're watching, and the one that we would insert into, say an equilibrium balance, like we did later in the unit, is the 2 silver ions plus 2 chlorine ions gives us 2 silver chlorides. Now, it's actually quite important to think that we need to reduce down, because if we don't reduce down, we'll have to think about how if we write this out as an equilibrium, as we did later in the units, right? If this is actually truly an equilibrium, not a one-way street like our solubility chart makes us think, then if you include those 2's, those are going to become squares on your equilibrium expression, and we don't want that. Okay, here's something we did fairly recently, was the balancing of this thing. I think actually this is from a section we didn't talk about. This is balancing chemical reactions in acid and base, and I think we're actually going to have some problems here. Is that right? Let me think about this. Well, let's see how far we can get, and then we might have some problems. So I've got an oxidation state of 0. I've got an oxidation state of +4. The oxygens are all -2 here. This is an NO3 minus, so I've got a +5 from my nitrogen here, and I have a +2 on my nitrogen over here. So I've lost 3 electrons, and the tin has gained 4 electrons, or has lost 4 electrons. So they want us to balance this. A little bit of a tricky equation to balance. So think about that the tin has gone to tin 4 plus 4 electrons. I like to use this system. The nitrogen has gone from +5 over to a nitrogen with of +2, right? So that means it's gained 3 electrons. And so to balance that all out, we would actually need to go all the way up to the lowest common multiple. Oops, I just realized these need to be on the other side. Let's see if I can cheat here. Okay. Can do a little bit of cheating. Okay, I think I got my cheat down. Okay. So I need to balance this by bringing it up to 12 electrons in total. So 12 electrons means I'm going to do 3 tins to get 12 electrons, and I'm going to do 4 nitrogens to get 12 electrons and 4 of those. And then I'm just going to pop that in and see what happens. I'm a little worried that I maybe have some problems here that I can't solve without resorting to some more complicated stuff we didn't do. So the idea would be to do something like this: 3 tins plus 4 NO3 minus gives us 3 tin oxides plus 4 NO. And I'm just going to look at this because I think we might have an oxygen imbalance here. We've got 12 oxygens on the left. We have 6 plus 4. We have 10 oxygens. So we ran out of oxygen somehow. There is a section we didn't talk about called balancing in acids and bases. And in this case, we would probably balance this with an acid. And, you know, this is getting into a place we didn't cover, so don't worry if you don't know what's going on. But I would essentially need 2 waters here. And that would be my other 2 oxygens. Okay, yeah, so I would say we have to kind of cross this one off. We can't really do that question because this is an in acid, and we didn't learn how to do that yet. Oh well, maybe next year. Whew. Okay, I think I'm going to stop this video now and come back and finish the kinetics and the rest of the unit after I take a quick water break.